about some joint work with Niko Naumann, which is still not available, but hopefully will be very soon. And it's divided in three parts. In the first part, I want to introduce what are several algebras in the context of city geometry, and in a notional degree, because it's going to be quite important for today's talk, and give lots of examples and motivation why we should care about these kind of algebras. And the second part will introduce notion of finite covers and introduce a little bit of Galois theory in the context of city geometry. And this is and then we're trying to connect the two works and actually and present one result which has several applications. So I give up one version of this talk, I think it's free, and maybe some of you have already seen that version, but now there are more applications. So if I have time, the talk will be different. Okay, so the setting is as follows. I said that I was going to introduce all this gadget in the world of city geometry, but I lied a little bit, because actually it's quite important to, at least for some part of the theory, to actually develop a theory for stable infinity theories. So C will be optimal stable homotopy theory. And this is just an announcement of a compactly generated tensor triangulated category. So note that I don't assume that dualizable and compacts are the same. And often I will have to consider the small version of this. And one example of this will be always the dualizable. And this is a two-ring. And this is an enhancement of an idempotent complete. Essentially small TP category. So sometimes I will have to actually impose some smallness conditions, so it's actually work in this context. Some other times I can use the big version, and I will be a bit sketchy during the talk which one I'm actually using. Okay, but maybe let me give the first definition. Okay, so this is Balmer. So I can take a commutative algebra and see. It can be a big version or a small one, it doesn't really matter. It's separable if the multiplication map mu as a bimodule section. A bimodule section. So this might be a slightly strange condition, and let's look at some examples. So the first one is if your commutative algebra is idempotent, so the multiplication map is an equivalence, then you can always pick an inverse, and that will also will provide a bimodule section. So algebras, this simply means that mu is an equivalent, and these arise as a Balmer localization. So if you have a Balmer localization, Smashing localization of your C, then you can look at the image of the unit, and that will be an idempotent algebra. So this is one source of examples, but actually we have many more. So maybe this is due to Balmer. So we can look at a separated etale morphism qcqs schemes. And yeah, and then we can look at the push forward of the structure sheet of U, and this is separable in dx. And in fact, there is a stronger result by Naumann. So under the additional assumption that x is Noetherian, then the only separable algebras that can appear in the D of x are either the form 1 or 2, are the combination of things which are in 1 and 2. Then Naumann. Okay, so this is a very nice result. So we have a nice classification result for separable algebras, commutative algebras in the right category scheme. But we have many other examples, so coming from different fields. So if J is a finite group, and let's say K is a field of characteristic P, then we can look at what is usually by AHG. So this is just the free module G mod H. And I can look at this as a commutative algebra in the stable module category, the small one. And this is, I guess this is again Balmer. This is again separable. For any H. And we also have in this equation, so we know that if G, well, if K is separably closed, and G is a cyclic P group, then we have a classification result by Balmer and Hausdorff. Showed that the only separable algebra that you can find in these settings are precisely those which are finite products of these guys, or the retracts of those. Showed that and separable algebra in mod, that's the small version. Finite product of these. Okay, and there is another, since this is the equivalent week, I should also give another example. So if now it's a G compact Lie group and H is closed subgroup. Then I can look at the dual of G mod H plus. This is now commutative algebra in this spectra. And this is separable if and only if the index of G mod H is finite. And this is a combination result of Balmer, D'Ambrosio, Sander, and the result of Sander.
Luca, can I just check? So,
Yes.
AGH,
Yes.
you're viewing that as a co-induced thing, so that it's commutative algebra?
Yeah.
It's not as a group ring, so
Yeah.
it should rather be like a
Well,
dual
you can be very explicit. You can really give the formula for the multiplication.
Right, but this uses a diagonal map on G.
Yeah. So one way to see is that this is the induced module, but it's also isomorphic to the co-induced one, and the co-induced one will have a structure. So yeah, which is also here. Okay. So I think, so these are lots of examples of separable algebra. You can see that maybe these two are quite similar. So what we are doing, we're taking the unit object, for example, in spectra, and then essentially apply symmetric monodal functor to it. And symmetric monodal functor will preserve separable algebras. And these are, I guess, the best way that we know how to construct separable algebra from the one we already have. But as far as I'm aware, these two are just the only separable classification result that we have. This one and this one for separable algebras. There might be others in the literature, so I'm not 100% sure, but at least this one, the one that I've encountered. But in general, we don't know very much about them. So we have examples, but not the full classification. And so maybe, let me say, why do we care about this? And I think there is maybe a more philosophical point of view, reason, motivation, and maybe a more, and maybe another one, different flavor. So the first one is, if we look at name as a result, we can see that separable algebras are very close related to the etale topology. So if I ask the commutative algebra to be compact or perfect and separable, then it will be precisely these guys here. Will be precisely those coming from finite holomorphisms. So in some sense, the study of separable algebras of C is closely related to studying the etale topology C. And we will see later on, hopefully, that this is actually quite, in many situations where we have a notion of etale topology, then this is actually true. And maybe the second reason is that, so if you're interested in stratification, for example, so classify and localize in a thick tensor ideal, then separable algebras are quite helpful because they allow you to descend stratification. So separable algebras useful for descent results. So there is another reason why we might care. Okay, so we have the definition, we have some examples and a little bit of motivation, and now I want to introduce the notion of degree, which is maybe a slightly technical condition, but it's actually quite helpful when you start working with this kind of gadgets. And so let me maybe go into this construction. Which is originally due to Balmer. So let's take a separable algebra. Then there is a tower. Let's start with the A0, goes to A1, A2, and it keeps going. You might not stop. And so A0 is by definition 1, the unit, and A1 is A, and this map is the unit map. And then we can define the others by induction. So for n greater or equal than 1, then we can define the n plus first piece to be the essentially unique A-n algebra such that two things. So if I take A-n and I smash it itself, over the previous guy, so an minus first. Then there is a small lemma that which is hidden in this construction. This always splits as a copy of an times something else, and I define that something else to be n plus first. And there is a little bit, so the splitting is actually satisfy the following. So if I do h, and then I project down to the first component, then I should get the multiplication map. So if I project, say, apply h with this equivalence, I project down here, then I should get the multiplication map of an. So it's not clear why this is always true, but this is part of the condition of A is separable. If A is separable, this is if A is not separable, then this is not going to be true. So maybe let's just put two examples here. So you can check that. So the degree. Wait, I understand the degree. Then I can say so A at finite degree n greater than or equal to 0 if the nth piece of this power is non-zero and the next one is 0. Okay, so I know the power eventually is going to be 0, and if not, if I know that all these pieces are going to be non-zero, then I set the degree of A to be infinite. So this is some sort of notion of how big your separable algebra is.
Sorry, what map are you taking? No. N-1, okay.
The tensor product, I mean. Yes.
I read N+1.
No, it's minus 1. Yeah.
Are the ANs also separable?
Yes. Because I think you can prove the tensor thing if you tensor two separable things, they can tensor separable, and then retract those separable and inseparable. So yeah, this is why you can do the induction again. Oh, there's a lot of water in here. Very good. So one thing that you can check is that the degree of A is equals to 0 precisely if A is 0. Because I'm asking A1 to be 0, and A1 was by definition A, right? So there are two easy examples. The degree of A is 0 if and only if A is equal to 0. And degree of A is equal 1, so this means that it doesn't have degree 0, so A must be non-zero. And then I know that A2 is 0. A2 is 0, so if I tensor A1 with A1, which is A, I get A. And this projection was the multiplication. So you get the mu as an equivalence. So A idempotent. And this is an interesting condition because so if your separable algebra is finite degree, then you can do this induction to prove statements. So you first check it for idempotent things, and usually it's quite easy, and then you try to do some induction algebra to get the general case. And maybe since I have it here, you can check that the degree of this algebra here are precisely the index. So in that sense is is the size of the separable algebra.
Precisely what?
The index.
Okay. Okay.
G mod H and G mod H.
Thanks.
Okay. And so this is the global, if you want, notion of degree, but there is also a local one. So if you have a nice prime ideal, in let's say your Balmer spectrum, then you can look at the local category. This is a functor QP from C to the P local category, which is defined to be, take your C, you kill the prime ideal, identity complete. And this is again a TT functor, and then you can define a nice degree function of A on the whole Balmer spectrum. It goes to Z union infinity. Well, maps P to the degree of A, the degree of QP of A. So I look at the image of A here, and I calculate it. So now it gives me a function on the Balmer spectrum, and it's kind of interesting to understand what's the behavior of this function here, generally.
Luca,
Yeah.
can you give an example of something that is degree infinity?
Yeah, exactly. So this is there are no example known. So this is a very strange condition that, well, it's kind of helpful to have it, but at the same time, no one knows examples. And I try to think about this a bit, try and find a concrete example in weird situations, but apparently it's very difficult. So I will ask, in many of the results that I will put on the blackboard very soon, I will demand A to a finite degree, and that's a condition, but it's almost always verified, at least to other examples.
So are you here in the setting that all objects are dualizable, or are you allowing kind of bigger objects here?
I think for this definition you need some smallness, so I think here you are in a two-ring situation. Yeah. I even have to take a Balmer spectrum. A little bit. Okay, and so maybe before moving into Galois theory, I just want to put this question. So can we say something about the degree of A as a function and A? So for example, we always know that the degree function is always upper semi-continuous, so it's not a completely random function. But so it's kind of nice to know if I have a little bit of information about this degree function, can I deduce something about A? And the answer is yes, in some cases yes. But let's wait a little bit, because it's going to be the third section. Okay, so this is one part of the story. So we're interested in classifying separable algebras in many categories. There are many classification results, and we'd like to get some of those. And there's this nice degree function which is associated to any separable algebra, and which we would like to understand a little bit more. And we can use this, we can try to understand this separable algebra using Galois theory. And to do so, I need to at least introduce a little bit of notations and terminology. So here is the 5 covers in Galois theory. So let me start with a definition, and then we will try to relate this definition to the previous one. So this is, I think, originally due to roughness. At least the version that I'm presenting on the board is due to Matthew. And so now we can take a commutative algebra as before in C. And here really being the big version. Then A is a finite cover. If two things are satisfied, if there exists A prime, another commutative algebra in C, which is descendable, this simply means that if you take a thick tensor ideal or generated by A in C, you get everything.
A prime.
A prime, yes. Very good, thank you. So if sometimes A prime will be dualizable complet, and then this condition can be checked on support. The support is everything. Okay, and an equivalence. So if I base change A along A prime, then this is the composition in A modules. Then this, I can write this as a bunch of copies of A prime, a finite number of them, up to some idempotent, so I can up to retrans. So I can take some idempotent for some idempotent EI. So whenever if I base change A along A prime, then I get lots of bunch of copies of A prime. This is and the second definition. Oops. So A is a faithful G Galois. It's just let's do this. It's faithful G Galois, so G is a finite group. Wait, I missed something. So now G is A is not just a commutative algebra, but it's actually a bit more. It's a commutative algebra of an action of G. It's faithful G Galois. If three things are satisfied, so if I take the fixed points, I get a unit of C, and again, there, if I tensor A with itself, then I get a bunch of copies of A, but now index on G, and faithful. So A is faithful. So tensor with A is conservative.
So at the beginning, C was just it's a tensor triangle in category, right? So that was something in the homotopy category.
No, yes. C is always like a stable, presentable. Yeah.
Okay.
It's always infinite. Everything I said. There is a version, but there is a story for separable things. It's only being worked out in the TP category. But then what we do with Niko is actually check that everything works out for infinity category as well. So the story that I said that told for separable algebra also work in a second. And this version here in this paper by Matthew about Galois theory is only, it's for stable infinity category.
Okay, so from section 2 onwards, we are now taking C to be a stable infinity category.
Yeah, but also section 1. It's always.
Right.
Always.
Okay.
Always. I think sometimes it's
okay, but but some of these are equivalent to doing it, like you can, this section is equivalent to finding it in the homotopy category to finding a strict one, or what?
Well, if you find a section in the level of infinity categories, then you also have at the level of homotopy category. I think the other way around is not straightforward. I think.
Usually, of course, it's not. Equivalent, but I thought it with this particular thing.
Yeah, well, I think it's. I think the answer is people say that it's true, but I don't think there is a proof of this statement. Because what you're asking is that.
But Balmer's original definition was in the homotopy category. No?
Yes, yeah.
Okay.
Yeah, but I think it's not immediately clear, at least to me, that if the statement is true for the monotony category, then it's also true for the infinity category.
Okay.
Because you have to ask that A is a retract in A tensor A module. That's pretty much the condition. And in the multiplicity of A tensor A module is not the same as modules in a multiplicity of A tensor A. So there is a bit of issue that you have to be careful.
These are separable algebras, so it's true.
Yeah, I know that's true. But still, I think that really still not enough. So I spent a lot of time trying to prove that if you have a section in the multiplicative, then you also have it for infinity categorically. But there was always something missing in them. So I don't know, if you have an idea, I will be very happy to.
I think my student Maxim Ramsey.
Yes, he told me. Yeah, he sent me an email yesterday, but I didn't.
Okay.
Yeah, but from what I understood, so he told me that he has a proof. I don't know the proof yet, but it wasn't obvious. At least from what I understood. The email was long. No, I raised the wrong one.
Couldn't you also have used algebras in the homotopy category that are separable from the come from a blocky infinity?
Well, so I think this is also true. So if you ask to set, in general, commutative algebra in C will be different than commutative algebra in the multiply category C. But if you ask them to be separable, then apparently this is true, but I haven't seen it. Like, if you see, well, then eventually, hopefully, I will give some classification results, and then you will see that in all the example, I mean, all the separable algebras comes from the multiply category, so it's at least believable. So we are so we have finite covers and faithful Galois extensions. Let me just say in words a few examples. So if you take a faithful Galois extension of field, you can check that it actually fits in this framework. So it's a nice generalization. But then you can also get some more exotic, if you want, example like the complexification map from KU to KU is one example, and there are many more examples of faithful Galois things. Maybe finite covers is something that people, I mean, it's not, well, maybe it's not much known, but we will see some example very soon. So let's maybe relate a little bit this definition to the previous ones. So first of all, if A is faithful Galois plus descendable, there was a condition about either the support descend or plus descendable, then this is a finite cover. And the second one, which I think is originally due to arguments, if A is Galois, then A is separable arbitrary the cardinality, the order G. So the proof is quite easy. I mean, the proof of A, let's just look at the definitions. So the claim is I can just take A prime equal A So I need to check that there's a finite cover. So I need to check that the A prime is ascendable, which is fine. It's precisely the condition. And then if I tensor A with itself, by the second condition that I get up G copies of A. So in this case, the order are just identical. So it's very simple. And the second one, let me really sketch the argument why is separable, and then the degree we just split it. So the idea is that we have this multiplication map, and we're looking for a bimodule section. So we can use the Galois condition and write this as a product of G of A. And so actually this equivalence is not a random one. There is a specific map providing the equivalence. So you can check that if you want to make this diagonal commute, and then what you need to put down here is the projection at the trivial elements of G. So then you can take the inclusion at the trivial element, and that's the bimodule section. So you need to check that, of course, everything is compatible and everything is nice. But there's it's a good idea that goes back to Robin. So faithful Galois extension are a very nice example of separable algebra. So this gives you other way to construct them. So, but you, yes, okay.
So when you write A tensor A as the product of copies of A, in what category is that?
Yeah, very good. In commutative algebras of A modules.
So I mean, the indexing by G doesn't seem to be. What is the?
If you want a co-induction, you can also, I don't know what the...
So I mean, how do you identify the identity component there?
The identity component.
If it's just an isomorphism in that,
Yes.
G isn't there.
I'm just saying that this is a G copies of A, right? It's
Yeah,
a
so
ring.
which is the identity component?
Which is the identity component?
You have
It's
a
a
map.
cardinality of G components.
I don't think
I mean, you're thinking of a particular indexing of those components by G?
Yes. I mean, I don't think I understand the question.
No, I think this map is not really clear what you have there.
This map is not.
The map which you consider it's not clear really.
Yeah, I mean the map is supposed to be A1 tensor A2 maps to the component G is A1 and then you apply G to A2.
Oh, okay. Good. Now I understand.
Okay. Right. Yeah, so why Galois theory? The idea is of Galois theory is that we have Galois correspondence. At least in this version is usually marked, which proves a more general statement, but let's just write this one. So C is a stable multiple theory. Let's say that phi 0 the unit is in the composable is a ring. This is the condition is not necessary, it's just to simplify a little bit the statement. Then there exists a profinite group phi 1 of C, which is the Galois group of C. And an equivalence between the finite covers of C and finite sets. Well, these are finite discrete, finite discrete set with a continuous pi1 selection. So, in the example that we will see very soon, this will always be a finite group. So these are just finite sets, so very nice. And the Galois correspondent tells you that we have a really nice understanding, at least in theory, of this subcategory of finite covers. Because these I can always see them as finite sets over some profinite group. And so on the other side, we were interested in understanding separable algebras, and that we saw that it was actually quite difficult to understand. So the punchline is that this category actually is more accessible than separable ones. So it would be very nice if we could show that there is a relation between these two, because this one Matthew developed lots of tools to calculate this side here, and so if you can understand this quite well, and hopefully you can understand this side very well. Now maybe if you think back at the beginning when I gave some example of separable algebras, for example, the stable module category, or in G spectra, you can know that they arise from cosets, right? So it's kind of, again, they come from some finite sets, a category somehow.
Sorry, what's the declaration of the C alg? Can we?
Here, or this
Statement of the theorem. Yeah.
this cover, finite covers. Yeah, so. So I think it was somehow known that there should be some sort of relation between the finite cover and separable algebras. But I think no one actually knew the precise statement. I mean, yeah. So, and this is maybe our contribution. Let me spell the name correctly. So let's say that C is a stable homotopy theory. And there is some technical condition, but let's say with phi 0, 1. I mean, I can say indecomposable, but actually you can just say that it's a finite product of indecomposable ring. So for example, if the ring is in a p-n, it's fine. And in most of the cases it's going to be connected anyway, it's going to be indecomposable. Then the finite covariance C are, I'm going to explain, but these are precisely the separable dualizable algebra with a locally constant and finite degree function. So we define covers and this separable dualizable commutative algebras with locally constant and finite degree function. So I had this question at the beginning that said, so if we know something about the degree function, can we deduce something about A? And then this is one possible result in that direction. So how much time do I have?
15 minutes.
Yeah, okay, very good. So maybe, let me just say words how to improve this. Because some of the idea is not completely, I mean, it's not very difficult once you know what you have to do. So if you have a finite cover, so the idea is, whenever you want to, in Galois theory, if you want to check something, you first check for the faithful Galois extension, and then there is some general technique, non-trivial, but that allows you to get a statement for finite covers. So then you can just check for finite, for faithful Galois extension, and we've already seen that the separable of finite degree, there was the derived G, is dualizable. This is also a very sort of statement, and Robin has already proved this. And then you have to check that the degree function is locally constant. And this is where you have to use the fact that you can base change your A along A, and it's become just a product over G of A. And you check that you can actually, the degree function, if it was locally constant, then it also stay locally constant once you base change. But now you have just a product of the unit, and the degree function is just constant, locally constant in that case. So you can deduce this sort of direction. And this one, so we know that if you're a finite cover, you're always, well, the fact that it's dualizable, so the backwards direction is a result by Powell's, some actually ideas of Powell's, that kind of show that you can reduce the constant case, first of all. So let's assume that your degree function is constant, and you have finite degree d, then so finite degree d and constant degree d, then you can, so the e prime that you need to take is the d part of your tower. Yeah. So then you kind of need to verify that this is actually the guy that splits your A, and it is there's something to check, but it is doable. Okay. And so why this result is helpful? So let me give you so one application, and then we see how much we have left. So I think the nuts is, I mean, you just want to apply this result and get some easy statement out of it. So, and the first example you can look at a finite group. And let's take K, a field of characteristic P. Let's say dividing the order of G. And maybe let's say this has separably closed. Then we can look at the Balmer spectrum of the stable module category. And this approach of the homology ring. And you can, so the easiest, I would like to, so this locally, I don't like this locally constant condition. So if the Balmer spectrum was a point, then every function out of it will be locally constant. So then you can check that this is just a point, if and only if as G is a P rank 1. So this means that the maximal elementary abelian P subgroup of G is rank 1. So in that case, we know that the separable algebra in the small version of finite degree. So the finite condition will always stay, unfortunately, but we said that this wasn't really a strong condition. These are precisely the covers of big version. And Mattia has already calculated this one. So we actually know what this is. Oh wait, let me actually, well, yes. So we know these just finite sets. There must be an op somewhere. Let's put it here. Over W. So what is W? So I have a G is a P rank 1 group, so I can take the P figure. The elementary building G maximum elementary building is a group. So this is by the condition of having rank 1, it's just mod P. And we can just take the value of this. So W is the value. Of P and G.
So that you mean the normalized modulo of P?
Yes, exactly. Very good. And okay, so this was Matthew's result, but it wasn't clear. I mean, this is an abstract equivalent, so it's actually not clear what was. So if I take W here, what is the gadget on this side? But so we also managed to explicitly give the map. So this is going to map W to this APG, which was K of G mod P. So you kind of look at, so this is a W torsor here, and W torsor will correspond to faithful Galois extension. So you need to check that this is a faithful Galois extension. And then you know that any orbit here is just a multiple orbit of W. So then everything else is going to be a multiple fixed points of this guy. So if I take a U, so close up here, I can write my U as V mod P. And then this is going to be mapped to A V of P. So we have a very explicit equivalence here. And in particular, there was a question by Balmer and Carlson that asked if it's true that any separable algebra in the stable module category has this form. And well, if you add the condition that they have to have finite degree, then at least, so before we only knew the statement for cyclic P group, so now we know a little bit more. We know that it's true for any P rank 1.
In this kind of your gong show, does this depend on the definition of the while group?
I think this is the only byte who's going to work, for sure. I think, yeah. I think it's only this one.
So this is a composite of two isomorphisms, right? Where the first one is Matthew's isomorphism, and then the second one is the one from your theorem, right?
Yes. The thing is, both of these are very abstract. So there are two statements, right? So this is the theorem there, and this is just essentially Galois corresponding with a little bit of work. So and is a result. But I think it's not clear whatsoever what W goes to. So but the machinery tells you that everything it must be this, and then you have to construct an element, right?
But was that also not clear in Matthew's work, or where is the?
I don't think he was.
Okay, I see.
I think he proves that this equivalence, but I don't think he proves this.
Okay.
Yeah. But it's possible they proved it. Well, at least I read the paper and I didn't find it.
Okay, right.
Maybe someone else reads it, but
okay, no.
But it's mine. So this was, but in spring when I gave this talk, then I was asked, can you do other examples? Can you use Galois theory to deduce some more example of, to classify some more example of several algebras? So then we sat down, we tried to prove more classification results. So maybe the second example that so we can look at so now an infinite ring spectrum. And then we can look at the category of covers over 0A. So this is just the category of finite etale pi0 algebras, pi0A algebras. Then in this situation, we always have inclusion between the covers. If you want the right ones, these abstract ones which are defined, and the separable and realizable ones, separable and realizable, so over the perfect modules. Right. So this is well, essentially is part of our result, and this is I guess this is pretty much due to Lurie. Oh, this is probably classical, but it's Lurie Matthew. And so then you can ask. So Matthew proved that in many situations, for many choices of A, this is an equality, not just an inclusion. So then what we try to do is, okay, can we check that this is also an equality in this situation? And yes, and in many cases, so you can actually do that. The theorem. So we have these ones are just separable. So here we managed to do something a bit, we can do better, so we can remove the finiteness. What's that say? Equality if one is connected, infinite ring, and 2 if A is even periodic, infinite ring with pi 0 of A, yes, is regular in the theory. So at the beginning I said that understanding separable algebra was close to understanding the topology. So in this context we know there is a notion of etaleness, and again, it seems to match quite well. Yeah. So maybe just you can ask, so what are the ingredients here? The idea is, I mean, the main ingredient I think is always main ingredient. Essentially, what you need to do is because of this series of inclusions, if you take a separable perfect algebra, then you need to check that this essentially etale, and then the map from pi 0A to pi 0B is finite. So this is something you can do by, at least in these cases, by reducing everything to the residue field somehow. So the main ingredient that you need to know is that you need to know what are the separable algebra in the right category of a ring, of a field. Well, I think this is classical, but at least I learned this from a paper of Naumann. And maybe let me just conclude that so we also know that this factor of covers actually commutes with limits. So every category is a limit of modules over infinite ring will also have this kind of nice property. So in particular, we can slightly improve in some sense a Naumann result. So if X is a quasi-compact quasi-separated scheme, then we also know that the separable algebras well, in a category of quasi-Coulomb Schubert X So here again, finiteness of the degree has disappeared. This just the covers. And these are controlled by the Carl fundamental group of X. So you see that we dropped the condition that was Noetherian, but we only classified the perfect algebra. So we gain on one side what we lose on the other one. And I'll stop there.
Could you just read what that said?
Yeah. And these are controlled by the Carl fundamental group.
Thank you.